So I'm Andy Foden. I'm a Senior Bridge Evaluation and Technology Manager with WSP. I'm going to be talking about the use of advanced bridge evaluation techniques for the Blatnik Bridge. So the outline for my presentation, I'm going to talk a little bit about the bridge and its significance. Then I'll talk about a study that was started back in 2015 by MnDOT and WSDOT called the Blatnik Bridge Management Study. And then a follow-up work that was the technical analysis, which did LRFR rating, lateral wind force analysis, material data collection, service life analysis, and then present my conclusions. The Blatnik Bridge is located between Duluth, Minnesota and Superior, Wisconsin, and crosses over the St. Louis Bay. It's a very important bridge for both MnDOT and WSDOT, and particularly for MnDOT, it's the second longest bridge in Minnesota, and it's right adjacent to the Duluth port, which is the largest on the Great Lakes, with over 900 vessels visiting and 35 million short tons of cargo passing underneath the bridge. It carries 4 lanes of traffic, 2 in each direction, with almost 34,000 vehicles a day back in 2013, 120-foot navigational clearance, total of 52 spans with a total length of almost 8,000 feet, 2 cantilever deck trusses, 270-foot spans, and 1 through arch truss cable-supported deck with a main span length of 600 feet. So in 2015, MnDOT contracted with WSP to undergo a management study for this bridge. And the goal of the study was to help MnDOT and WSDOT make decisions about the future of the bridge. The study was based on adding additional 15 to 40 years of service. And our goal was to identify investments that must maintain better than structural deficient condition, and to continue to allow Minnesota seed permit loads of 159 kips to pass over the bridge. While out on this bridge, I've seen a lot of wind farms that are going up, and the components for those are often going across the bridge, and there's some pretty heavy loads. We had to minimize any service interruptions for any of the study options and provide a framework for other MnDOT bridge studies. So we developed a series of strategies to maintain the crossing. We identified actions and investments to support those strategies, including quantifying the effects of traffic interruptions, identifying and quantifying risk factors. Each strategy was evaluated by life cycle cost analysis, and goal was to provide a tool for MnDOT in future making decisions and to investigate options for a potential truss-only replacement. So the recommendations and associated costs were evaluated, including maintenance recommendations, rehabilitation recommendations, and replacement options. The scenarios developed were for 15 to 40 years of service life, with 12 different scenarios developed and fully evaluated. Road user costs were generated for each scenario, and life cycle cost analysis was performed and a net present value generated. The results of the study were presented in a final report and provided tools for MnDOT to use to guide future actions. As part of the study, we compiled and archived existing bridge data, determined conditions using only the existing data. We had inspection reports, both routine, fracture critical, and underwater. There's plans and specs from the original construction, a rehabilitation that had been done, and a widening that was done in the 80s, where they added shoulders on the approach spans, but could not add shoulders in the truss spans due to geometric constraints, and to do a historical special investigations. Part of that study also identified information gaps in the existing data. We only had basically visual inspection information, and there's a lot of things that were unknown and that we really couldn't quantify well for making long-term projections. So taking those gaps in that study, after they were determined, in 2018, that led to the technical analysis project, which I'm going to focus on today. The main goal of that project was to fill in the knowledge gaps. using more quantifiable information to understand the load carrying capacity, the wind behavior, and the deterioration of components due to corrosion, the deck, superstructure, substructure, and footings. I'm going to focus today on this concrete element since this is ACI, but we also did the evaluation of the steel. To determine the load ratings, we did LRFR load rating. We used BRR only for the stringers due to the complexity of the structure. And for the trusses, we had both the 2D and 3D models that were developed using Midas. We calibrated our models to account for the sequence of construction, and all components were rated, including substructure components, because of the potential reuse of substructure for future projects. To further validate the models, with the truss, there's always assumptions made. Is it a pin connection? Is it fixed? Is it somewhere in between? How do we model that? It does have an effect on the rating. And also, with the complexity of the approach spans, with the widening, how does the widened structure distribute load with the original structure? So we evaluated this doing load testing, and this is done in conjunction with the University of Minnesota Duluth, and our moderator, Ben, was part of that along with his students. And we did a load distribution in areas with complex framing. So if you look at instrumented area in span 1, this is where we have curvature, we've got skew, and we've got widened girders next to the original girders. We looked at a composite action of stringers in both negative and positive moment areas. And then we did a little bit of an evaluation of limited truss member restraint. The results of load testing showed that the FEM models overpredict the bottom flange stresses and fairly significantly, and models underpredicted local load distribution between stringers and girders. So by calibrating the model to the load test, we were able to get higher load ratings. Composite action in the built-up girders varied based on the distance to the applied load, and we really couldn't make very good conclusions about the truss restraint because the loads that were applied were relatively light. In a truss, most of the load is from dead load, and the live load has fairly minimal effect. So when we get into the material data collection, we did a very thorough evaluation of the deck, which had to be done with minimal disruption to the traffic. There were some ongoing lane closures with very limited windows during the biennial inspection that was being done, but primarily we had to work without any kind of a permanent traffic closure. So we worked with InfraSense and BDI to collect data with vehicle-mounted NDE methods. So we had high-resolution video, infrared thermography, and deck acoustic response. Data was collected using mobile work zones at up to 45 miles per hour for the high-resolution video and the infrared thermography, and the deck acoustic response, or SOUNDAR as BDI calls it, was limited to about 5 miles per hour, so it was a moving closure. All of this was validated using limited destructive testing and allowed lane closures, and also we took cores to evaluate the chloride concentrations. And I'm going to present some selected results. For the most part, we found this bridge deck was in excellent condition. There was quite a bit of transverse cracking, those shrinkage cracks from the original construction. The cracks had been filled by MnDOT very early on, and we found that sealing of the cracks has been performing very well, although there is some local efflorescence. For the most part, that deck treatment had performed as expected. The top section here is probably the worst section. This is showing the GPR results. And you can see that there is some area of active corrosion, which is what GPR typically tells you. This is also overlaid on top of the high resolution images of the deck surface, as well as the infrared, the lamination. You can see that the lamination areas are very limited and very small, and are likely, we believe, not due to corrosion, but more correlated with stress cracking. The results from the deck acoustic response, overlaid also on the high resolution video images of the deck surface, you can see there's a similar amount of very localized potential delaminations that correlates very well. If I go back here, if you look at the red patches on this slide, which is the infrared, and then looking at the colors on this plot, which is the deck acoustic response or impact echo, is a very similar pattern. We found very good correlation between those two methods for this bridge. When they widened the piers back in the 80s, they used post-tensioning to extend the pier caps. And there was a variety of different ways that they did that, and based on the pier and the widened section. Here's one typical one. And on the left side is a pour back that we removed locally and exposed to evaluate that. The red areas are where we did local exploration to validate the NDE results. But the process was to locate the tendons using GPR. Then we used sonic ultrasonic response to determine areas where there was no grout or suspect grout. We would probe in and take grout samples and evaluate them for chlorides, and use a borescope to visually inspect the openings. And here's some of the results from the material data collection. So you can see in each of these 4 locations, when we went in and exposed the tendons, that there's virtually no corrosion on the tendons. We've got sound grout, and that when we did the chloride evaluation, there were very low to minimal chloride. So the protection of the strands is doing its job. Another interesting thing we found with the aggregates in this area that was pointed out to us, this work was done by NDT Corp. And they had pointed out when we were on site one day that the pieces of concrete that they were removing were actually magnetic. And we did some investigation and found that the aggregates in that area had quite a bit of iron in them. So you could actually pick up the concrete that was being drilled out and pick it up with a magnet, because there's enough steel in it for the concrete to be magnetic. That's quite interesting. And when we exposed the anchor plates for the post-tensioning, and obviously this was a just partially destructive test, we found that the reinforcement had no visible signs of corrosion at all, that they had been well protected and were in excellent condition. And then finally, we did a service life calculation. So we used all the information that was collected from the impact echo, from GPR, from infrared, the high resolution video, and our chloride samples. And part of that evaluation was to understand, using the GPR, the cover depth, because in order to do a proper service life evaluation, you need the cover depth and you need to have it fairly accurately. And what this figure is showing, so we have the Minnesota approach, which is the red line, the main span truss, which is the blue line, and then the Wisconsin approach, which is the gray line. And then the dashed vertical blue line is the age of the bridge when the evaluation was done, which is just about, of the deck, which was about 25 years at that point. The gray area is when bridge decks typically are in need of significant repair and or rehabilitation. It's generally accepted, but somewhere between 9 and 13% is where an intervention would be needed. And when we projected that out, we found that at about 40 years is where they would need that intervention, 40 to 45 years. So there would be significant maintenance needed in the near future. So we fed all this information that was collected back into that previous framework developed in 2015, which we filled in the knowledge gaps with the more quantifiable information. And we found that the comprehensive evaluation of deck showed that it was in very good condition. Both infrared and the acoustic response results indicate a very low level of existing degradation and delamination. The ceilings of the cracks in the deck appear to be performing well. However, from the life cycle projections, we did find that the deck will require a major rehabilitation in approximately 15 to 20 more years, which will impact the decisions being made about the future of the bridge. The detailed information collected was essential to feeding into the various service life models and calibrating the finite element models to achieve accurate and reliable results that can be used to make sound decisions about the bridge's future by both MnDOT and WSDOT.